Okay, so we'll start session 3 of fundamental of spectroscopy. So today I will be discussing about okay, so let's start.
झालं का? हे बंद कर.
Okay, can you see my screen? Okay, I will starting now. Okay, so today we will discuss about rotational spectroscopy. So first we will see like rotational spectroscopy comes in what region of electromagnetic spectrum. So you can see here, this is the electromagnetic spectrum, and if you're going left, we're plotting against increasing of the wavelength, and this is increasing energy, or we can say frequency. So we saw in the lecture note that see microwave comes here, say around 9. So the range for frequency range for rotational spectroscopy comes in the range 10 to the power minus 9, 10 to the power 9 to 10 to the power 12 hertz, and this is microwave region. So that's why we call rotational spectroscopy microwave spectroscopy. So if you see here, in a molecule there can be different transition. For example, let's say we can see the transition between electronic energy level. Transition between electronic energy level. So if you see the energy difference between this transition between electronic energy level, and that is delta E electronic, which will be much higher than energy difference between two vibrational energy level. So that we are representing delta E vibrational. And further, the energy difference between two rotational energy level is very small than vibrational. So the conclusion is, if you can see this expression, we can draw the conclusion that the energy difference between two electronic energy level is very high compared to two vibrational energy level and then two rotational energy level. So today's plus, so first we saw here like this rotational spectroscopy comes in this range, and the second thing we saw, the energy level is very less compared to these two, and the third, so today's plan will be to discuss rotational spectroscopy. Okay, so the rotational spectroscopy means, let's say we have two molecule, one here, one here, how this molecule is rotating around one axis, and how this rotation give rise to a spectrum, though all the detail, and why we are studying rotational spectrum, what kind of information we can get from here, we will see everything here. Okay, so the classical mechanics for rotational motion is very tough, so that's why you will try to find the analogy or correspondence between linear and angular motion. Okay, before going into the rotational spectroscopy itself, we will first understand the different kind of motion and correspondence between linear and angular motion. Okay, so if you see here, let's say we have particle here in the center, it's a red particle of mass m moving in along x axis. So velocity for this particle can be given as v equal to x dot. X dot represent first derivative, and that can given by dx by dt. But if you consider some particle is moving around a circle, see this is moving around a circle, okay, let's say it moved till this distance x. This is very small, so we can consider this arc as linear line because this is very small. Okay, so we are considering the x, and then we can write sine theta equal to x by r. Because this x is very small, so we are considering this straight line. So we can write sine theta, and since theta is very small, because this arc is very small, so in that case we can write sine theta approximately equal to theta. Okay, and this equation will be reduced to this equation. Now let's try to calculate angular velocity. Okay, so this angular velocity represented by omega can be given theta dot, it is d theta by dt, and the theta we calculated here, we substituted, we got b by r after solving. So this is one way. In other way we can calculate like this angular frequency is nothing but linear velocity divided by peripheral. Okay, so in that case we can calculate angular velocity as 2 pi nu, that is again b by r. So what did we see? We saw this angular velocity is directly related with linear velocity. See, with this radius r. Okay, now we understood about angular velocity. Now let's see how the angular momentum or linear momentum that is associated with motion of a particle. Okay, so first we will consider a particle moving on a perfectly circle. Okay, let's say one single particle, it extends with some rope, and this particle is moving around the circle. So in that case, for this particle, this is linear motion. For linear motion, momentum is defined as m is to v. Okay, but for angular momentum we have to define r cross p. Okay, so this r is this radius and the p is momentum, linear momentum. So simply we can substitute p by mb from this equation, mb, and we can got something mbr. How? We can write like m is constant, and we can write cross product of r to b. Okay, so we assume that like this L and omega cannot be in the same direction. Let's in the for circle case we can assume it's in the same direction, but for different molecule, some in molecular system, this cannot be in the same direction, because if it will be the same direction, then this cross product omega L will be 0. So it has to be in different direction for rotational spectroscopy. Okay, so if you see here, this mr is nothing but moment of inertia. So we can write, we saw there in with this thing in lecture notes, so we are just revising. Based on this you will solve problems. Okay, so what we got, L equal to I omega, and what we know, P equal to mb. So look at carefully, this is linear momentum related to mass and velocity. This is linear velocity, and the angular momentum is related to moment of inertia as well as angular velocity. You can see here. So this term is replaced by this, and this is replaced by this. Okay. So these things were beautifully discussed in the lecture notes, so you should go there. And now we will solve the problem. So before going into the problem, so we saw here what is the correspondence between linear motion and angular motion, how this linear velocity is related with angular velocity, how the linear momentum is related with angular momentum. And then I will consider a molecule. Okay, since we are dealing with rotational spectroscopy, so we will take molecule, diatomic molecule. Okay, because monoatomic molecule we saw here in the first case, this L and omega will be in the same direction for monoatomic molecule. So the angular momentum for monoatomic molecule will be 0, and for that we cannot do rotational spectra, we cannot record rotational spectra. So let's consider a diatomic molecule one atom has mass m1 and the second atom has mass m2, and the internuclear distance, that is bond length, this is bond length, bond length is capital R2. And there are two molecules, one is heavier, one is lighter, so we have some center of mass here, center. So from this internuclear axis this is not internuclear axis, this is the axis from center of mass. So distance from this to m2 is r2, while distance from this point to m1 is r1. So we saw here for for monoatomic, this L is I omega. So for diatomic, we can write like sum of 2i, I for particle 1, I for particle 2, and this angular velocity, let's say it's rotating like this, it's rotating like this. Okay. So because of this rotation we will have angular velocity omega, and we have two particles, one particle here and one particle here. So the moment of inertia for this both particle will be different because masses are different. So we can write expression like this. Okay. And considering rigid rotor means while rotation the bond length should not change. So for rotational spectroscopy we are considering rigid rotor. So for rigid rotor we derived angular momentum is nothing but under root j into j plus 1 h card, and the energy we derived like this. So this was derived in detail there. So what is j here? J is rotational quantum number. Rotational quantum number. Okay. So what is the meaning of j? So what can have the value of j? So if let's say j equal to 0, in that case energy equal to 0. You can substitute this j here and you will find energy equal to 0. So what is the meaning of this? Any guess? No? Okay. So for rotation, so E is nothing but kinetic energy plus potential energy. So for rotation this is 0. So you will have only kinetic energy. But if this overall energy is 0, total energy is 0, that means kinetic energy is 0. Sorry. So that means kinetic energy is 0. What does it mean? There is no rotation. There is no rotation. Okay. Now based on our first lecture of this rotational spectroscopy, we will solve few problems. This is the first question. Which of the following in linear motion is analogous to angle swept by particle? So what saying? So which of the following in linear motion is analogous to angle swept by particle in angular motion? So we will write like this. Let's say we have this axis, and let's say some molecule is rotating on. Okay. So let's say we have two atom here, one atom here, one atom here. Or simply we can make it simple, like let's say it's rotating like this. We have some single particle here, single particle here, and it moved from here. Okay, so it swept some angle theta. Okay, and this is r by traveling distance x. So this theta is analogous to what? Theta is analogous to what for linear motion? Any guess? Can you see my screen? Hello? Am I audible at all? Hello? Can you please speak up? So this theta is analogous to distance. It's a very straightforward question. It's discussed in the lecture 1. So this will be a correct answer. Okay. So next question. Which of the following is a tensor quantity? So this is simple like moment of inertia. We saw in the discussion. Okay. This is nothing but moment of inertia. So we don't need to discuss in detail this question. Third question. What is the SI of angular momentum? Okay. So angular momentum we can define like L, what we got, I omega, correct? You got this only, right? So this is nothing but your moment of inertia. Moment of inertia. And how can we define this one? We define simply m r square. So what is the SI unit of mass? It's kg. And what is the SI unit for r distance? It's meter square. And this is frequency, correct? So the unit for this is radian second. Radian per second. So we are considering only seconds because we are second. So what is the SI unit of L? It will be kg meter square per second. This last one. So simply we can calculate, substitute all the unit, SI unit for I, SI unit for omega, and then we can determine the SI unit for angular momentum. Okay. So these were some questions based on lecture 13, like based on first lecture of rotational spectroscopy. Like we simply saw the correspondence between linear motion and angular motion and how both are related. The next thing will come rotational spectroscopy. Okay, so the first question is, what is the condition of rotational spectroscopy? We saw like how we can deal rotational motion, how we can calculate angular momentum, how we can calculate energy, everything we saw there for any diatomic molecule. Till now we don't know what kind of diatomic molecule, but for rotational spectroscopy, what kind of diatomic molecule we need? So condition is we need molecule should have permanent dipole moment. For example, let's say we have HCl. Okay, so the electronegativity of chlorine is higher than hydrogen, so it will have delta minus, it will have delta plus. So because of this charge separation, we will have some dipole moment, and it will be denoted by this line. So if molecule has permanent dipole moment, then only we can do rotational spectroscopy. For example, if let's say we have diatomic, homodiatomic, like H2 or O2 or N2, see both are same, so there is no electronegativity difference between both atom. So the dipole moment for all the three molecule mu is 0. So for this you cannot do rotational spectrum, but for this you can do. How? Let's try to understand. Okay, so we are plotting like this. Okay, so let's say this is our molecular axis. So dipole moment is in this direction. So initially it will like go like this, at this point molecule will become like this after rotation. So it's rotating like this. Let's say Cl is here, hydrogen is here, so it's rotating like this, and then this, and then this, so it will go down again. Okay, so in this case you will have this configuration. Okay. So simply by rotation, the magnitude, like direction for the dipole moment is changing by rotation. Okay, and it's generating electric, I would say electric field, because you see this molecular rotation. So in summary, I will say the molecule having permanent dipole moment during rotation, it will generate electric field, and this electric field will interact with electric field component of light. Electric field component of light. So that's why I'm mentioning in the in upcoming slide we will show mathematically that why do we need permanent dipole moment. Here we are just drawing an analogy from this electric field, that if there will no this kind of electric field, then it cannot interact with light. Okay, so this will interact with light if this frequency of this fluctuation will be similar to the frequency of light, and then at that frequency transition will happen. So frequency for this should match with frequency of light. Okay, so one condition, molecule should have permanent dipole moment. Okay, and why we understood here. So here we saw in the previous slide, see the R, this energy if you will see here, this energy is related to moment of inertia, correct? What is this moment of inertia then? The next question comes, what is this moment of inertia? How can we calculate this moment of inertia? Okay, so we will see here. So first look at this side, left side diagram. Okay, so we have two diatomic molecule. We have diatomic molecule. One has mass m1, other has mass m2. Okay, okay, and the distance here is r2 from here, and this distance is r1. Okay, and let's say it's rotating like this along this axis is rotating like this with angular velocity omega. Okay, with angular velocity omega. Okay, so at center of mass, what can we write? Any idea? So what will be first total moment of inertia? I is equal to, we saw in the previous slide, it will be m1 r1 square plus m2 r2 square. So we can write this m1 r1 plus m2 r2. We can say this equation 1. Okay, so at center of mass we will have m1 r1 barabar m2 r2. Okay, any doubt till here? Any question? Can you hear me? Okay, I'll assume you have no any question. So this R, capital R, is summation of R1 plus R2. Okay, so we can write here M1 R1 M2. This R2 we can simply write R minus R1, and this one we can substitute here. We can calculate I'm not going to do calculation in detail, because this calculation is already done in the lecture note. Okay, so finally we got this moment of inertia using this analogy, using this calculation we got this moment of inertia. Okay, So what will be energy of expression then? What we got, I is equal to, it's nothing but m1 m2 m1 plus m2 and this r square, correct? And this is, we are saying, nu r square. This is reduced mass. See, for diatomic molecule the moment of inertia becomes like this. For monatomic, what we got, it's m r square, correct? This mass of one single atom, and this is, what is that, the radius of the, this is radius, correct? And here this r is bond length or internuclear distance between two atoms. So for diatomic energy we can write like this, but usually while doing rotational spectroscopy we plot in centimeter universe, like in wave number. So how can we convert this? So we know that from previous note, this is hc nu bar. So we can substitute this value, we can got something hc nu bar, it's a square 8 pi a square I j plus 1. This h will be cancelled out, so 8 pi a square I c j plus 1, and we call this b. See, initially we have started the correspondence between linear and angular motion, and from there we derived energy for rotation of a diatomic molecule. It comes like this. So what is b here? B is h 8 pi a square I c. This we call rotational constant. Okay. So these are the expression for energy. One is here and the second one is like here. So this is in centimeter inverse and this is in joule. Okay. And we also saw in the previous slide lecture, previous session, like why do we need to change the unit? Why do we want to represent in centimeter inverse? So all the discussion is there only. So you can have a look there. Okay. Now based on this expression, these two expression, we will try to solve few problems. Okay. So the first question is the internuclear distance or bond length of carbon monoxide. So we have carbon monoxide. The bond length is 1.13 angstrom. Okay. Calculate the energy in joule and in electron volt and then angular velocity. So we have to calculate through two things, first energy and second omega. Okay. So the expression for energy is, this is asking in joule. So it was h square 8 pi a square I. Okay. We saw in the previous slide. See this one. This is in joule. Okay. And j into j plus 1. So to calculate the energy, we need moment of inertia. Okay. And for diatomic molecule, moment of inertia can be written as mu co r square. Now we have to calculate the reduced mass, mu. So how we can calculate that? Mass of carbon, mass of oxygen, atomic mass of carbon plus atomic mass of oxygen. And these values are given here. See, it's 1.99 10 to the power minus 26 kg, and this is 2.66 10 to the power minus 26 kg. In the bottom I will take common this 10 to the power 6, so it will be 99 plus 2.66 66 10 to the power minus 26 kg. So this will go off, and the value for this is any question till here? No? Okay. So it will be 1.138 10 to the power minus 6 kg. Now we can put here all the values. So it's 6.626 minus 34 joule second whole square 8 3.14 1.138 10 to the power minus 26 kg. Okay. So what will be the value of J here? Any guess? The molecule is in the first excited state. So if you draw here the energy level diagram, so this is 0, this is 1. So this is your first excited state. The value of J will be 1. So 1 plus 1. So if you will calculate, if you once you calculate this, you will get something like 7.61 10 to the power minus 23 joule. And we know 1 joule is equal to 1.602 10 to the power minus 19 electron volt. From this expression we can convert energy into electron volt by dividing simply by this number. Okay. So it will be 7.61 23 joule 1.602 joule per electron volt. So you'll get something 4.76 electron volt. So from here we calculated the energy. Now we have to calculate angular velocity. So what is the energy expression in terms of angular velocity? Any idea? Okay, you don't want to speak up? That's fine. So for linear we have kinetic energy 1 by 2 mv square, correct? For angular we will have 1 by 2, and instead of m we will have I, instead of b we will have omega square. So omega will be 2 e by I. So from this expression you can calculate omega. See, we have energy here in joule, and we know reduced mass also. We calculated the reduced mass here. See, so by simply putting the value you will get something 3.2311 radian second. Someone is trying to join. Okay. So till here no doubt, right? Rasmi, can you please unmute your mic?
Yes, sir.
Yes, join. I was saying to mute. Okay, sorry.
Okay.
Can you mute your mic?
तो स्पीकर ऑफ करना है.
Okay. So the next question is, given HCl molecule has bond length, so we have HCl molecule that has bond length 1.27 angstrom. Okay, if we increase the bond length by 10%, let's say we say this, let's say x equal to this. Now what we are doing, we are increasing the x by 10%, so x will be 1.27 angstrom, plus we increase by 10% means 1.27 angstrom. 10% was 10 means by 100, so it will be 1.27 angstrom, and this is 0.1, so 0.127 angstrom. So what will be the value of this? 7, 9, and then 3, 1. So after 10% enhancement in bond length, our final bond length will be 1.397 angstrom. Let's say we call this y. Okay, and we are not changing mass of hydrogen or chlorine, so we are not changing mass for this. We are not using different isotopes, we are keeping the same, simply we are stretching the bond. So what will happen to moment of inertia? So moment of inertia we know I. Okay, so this is given as mu r square. Okay, so we are not changing mass, correct? And this mu is nothing but your m hydrogen into m chlorine divided by m hydrogen plus m chlorine. So we are not changing mass, so this will not change, this will not change, but we are changing bond length, that is we are changing r, and we see that this r is I is directly proportional to r square. So when we increase the bond length, this moment of inertia, what will happen? It will increase, correct? Option 1. So coming to the next question. So till here we understood like how to calculate the energy, what is moment of inertia, for diatomic molecule how we calculate moment of inertia. Now we will see the actual problem, like what is the condition for rotational spectroscopy. So those things we will discuss further. Okay, so like summary of lecture 14. So we saw they are using Born Oppenheimer approximation. So for any transition to become allowed, this transition moment integral must be non-zero. This cannot be zero. If this will be zero, that will indicate there is no transition is happening between two energy level. So this transition moment integral should exist. Okay, we saw there, and we derived this equation using Born Oppenheimer. Okay, and this is in, and we converted in a spherical polar coordinate, it become like this. So if we see the transition moment integral, it depends on two things. First is this dipole moment. Okay, so in the previous slide we saw that the molecule having permanent dipole moment, that will show or that will give rotational spectra. So from here we can understood why the molecule having permanent dipole moment will give only. Okay, because if this dipole moment will be zero, this transition moment integral becomes zero, and if this transition moment integral becomes zero, that means there is no transition happening. So we need non-zero dipole moment. We need molecule having non-zero dipole moment. Okay. And the second thing is depend on theta and phi. What is the theta and phi? Let's say we have diatomic molecule. One is represented here, this red color, and second is this second one. So we have diatomic molecule. Okay, we'll say 1, 2, and we have three axes: x here, y, z. So it's making rotation and it's making angle theta with z, and this bond length is r. Okay, and the projection for this bond length, this is projection making angle phi with x. So this r is constant during rotation. The bond length is not changing, right? Because we considered a rigid rotor, and rigid rotor bond length will not change. So what is changing then? This theta and this phi. Let's say it's rotating like this on a loop. In that case, the theta and phi is continuously changing like this. So that's why this integral will depend on a function of theta and phi. Okay. And for allowed transition, meaning this second term will be non-zero only when we will have this condition. Otherwise, the second term or the transition moment integral will be 0. In that case, the transition will not be allowed, or there will be no transition, we can say. Okay. So from this simply transition moment integral, we find two rule. First, mu should be should not be 0. Second, this condition. So this J prime is excited state, and this is ground state. So this delta J must be plus minus 1. Then only it will be allowed. Okay. So we have two selection rule now. We call this selection rule. So if someone will ask what is the selection rule for rotational spectra, then we can say the molecule should have permanent dipole moment first, and second, this condition delta J should be plus minus 1. Okay. So based on this analogy or based on this explanation, let's try to draw energy level diagram for rotational spectroscopy. You guys can see my screen, right? Whatever I am writing. Can someone please unmute and let me know? You can hear me, right? If you don't want to speak, you can write in chat box also. I will see there. Can you guys see my screen? Anyone? Hello. You can see my screen, right?
No, sir. Screen not so.
Now?
अभी भी नहीं हो रहा.
You can't see my presentation?
No, yes, sir. No, I can't see.
Still it's not visible?
Yes, sir, not visible.
Okay. Thank you for the confirmation. Okay. So if we try to draw the energy level diagram for rotational spectrum, so how we can draw? Let's say this is like increasing energy. So this will be
But sir,
first.
screen कैसे आएगा सर?
कैसे आएगा मतलब?
स्क्रीन सर नहीं शो कर रहा है
कुछ
आपका.
जो भी मैं लिख रहा हूँ वो नहीं दिखा रहा है.
No.
Okay. Okay, maybe I will stop sharing and start again.
Okay, sir.
Now can you see my slide?
Yes, sir.
Yes, sir. Up now.
Okay, thank you, thank you.
Yes. Thank you, sir.
Okay, so if you try to draw this, so energy expression is E is equal to, or we will write wave number is equal to B j plus 1. Okay, so this is j equal to 0 1 2 3. So what will be the value of energy? We can put here j, so it will be 0, and for this it will be 2 bar, it will be 6 bar, 6b, it will be 12b. So this is the energy level in rotational spectrum. So let's say transition is happening from here to here, from 0 to 1. So what will be the energy difference delta A here? 2b. Okay, and let's say because of this transition we are getting some line, so we are plotting here the intensity I versus this B, centimeter inverse. Okay, energy. So because of transition from j equal to 0 to j equal to 1, we got some line. Okay, and because of transition from 1 to 2, again we got some line. And what is the energy difference here? Again 4b, the difference between two energy level. So 6b minus 2b. Okay, and the third line, let's say transition is taking from a state 2 to 3. So in that case again we will get some line. Okay, and the energy, what is the energy difference between these two? So we can calculate 12b minus 6b, so it will be 6b. So what is the meaning of this? The first transition, that is transition from 0 to 1, we were getting at energy 2b, so this is at 2b. Okay, and this is at 4b, and this is at 6b. So in rotational spectrum we will get multiple lines, and the difference between two lines you can see here is 2b. The difference between consecutive two line is 2b. Okay, let me ask you one question based on what we discussed. Let's say we are making transition from 0 to 2. Will this transition be allowed?
Not allowed, sir.
Very good, because in this case delta j will be 2, so not allowed. Okay, very good. So from rotational spectrum, if you do rotational spectrum for some molecule, then from this difference between two peak we can find 2b, correct? And from this 2b we can find b, and once we find b, we will see in the incoming slide what we can calculate. So we will understand the importance of rotational spectroscopy, like why we are interested in getting b. Okay. So if you see here, the question is asking which identify the microwave active molecule. So what was the condition? The molecule should have permanent dipole moment. So first is HCl. So electronegativity of chlorine is higher than hydrogen, so obviously it will have delta minus, delta plus. So it has some permanent dipole moment, so this will be microwave active. Now second, CO. Again the electronegativity of oxygen is higher than carbon, so it will be delta minus, and here delta plus. Again it has permanent dipole moment, meaning mu not equal to 0. Here also not equal to 0. So this will be also microwave active. And the third and fourth, can you please tell it will be active or not? there is no electronegativity
No,
difference,
no.
correct? Both are same atom. So in both cases,
Yes.
our dipole moment will be 0. So these two will be inactive, correct? Simple problem. Now next question. Which of the following line is are allowed in the normal rotational spectra? Okay. So simply we know like delta G must be
1 to 2.
1 to 2, correct?
1 to 2.
And also 0 to 1 also.
Yes, sir. 0 to 1 be.
And
Yes.
these two will not be allowed. Understood, right? Okay, now we'll go to next question. So the energy of third rotational line in centimeter inverse is third rotational line. So first we have to understand what is rotational line. Although we discussed in the previous slide, so I will discuss again. So this is our energy level diagram, delta E, and we have one. So this we had 0, 1, 2, 3. This is A, and this is 0, 2B, 6B. This gap will increase. The drawing is not that correct because this gap should increase. And this is 12B. So because of transition from J equal to 0 to J equal to 1, J equal to 0 to J equal to 1, that is ground state to first excited state, that will correspond to
63.6, sir.
what is that?
63.6.
Yeah, answer is correct. But for others, I will explain. Answer is correct. Yeah. So this transition we call first line. Okay, and this is appearing at 2B, and the transition from 1 to 2 is 4B. And the transition from 2 to 3 is 6B. So asking third rotational line. So this is your first, second, third. Okay. For third rotational line, what will be the energy? 6B. And what is given here? This one. So we can multiply by 6 into 10 to the power 6 centimeter. So 63.6 centimeter inverse. Simple. Okay, now we will go to next question. The energy gap between second and fifth rotational lines. Remember one thing, when they will say rotational line, meaning they are talking about a spectrum. They are talking about this spectrum. So this is called rotational line. When they will say rotational energy level, then you should consider this one. So rotational line means whatever you are getting in rotational spectrum or microwave spectrum. So what is given here? The energy gap between second and fifth rotational line. So we will draw one spectra here. So this is intensity. Let's say this is first line, second line, third line, fourth line, fifth line. So this is 2B, 4B. The difference is 2B, always 2B. So based on that I'm writing 6B, 8B, 10B. So this is second line, correct? This one is your second line, and this is your fifth. So what is the difference between here? What is the difference? It's 6B.
63 point उतना ही आएगा सर. 6B.
Yeah, correct, correct.
63.6.
6B. So again, like we can calculate energy delta E is 6B, and we know here B is this much. So again 63.6. Next question. The first line in the rotational spectra correspond to which one? First line. So this is the first line. Na? So for the first line, what is the energy? 2B. So the answer will be 2B. Simple. First line. Now can you calculate this, the value of B? Okay, I'll do calculation, then you can match with yours. So between 12th and 6, okay, so this is 1, this is 2, this is 3. So instead of drawing a lot, we can simply use mathematics to calculate this. So how we can calculate that? Let's say we are saying first line, meaning the transition is taking between j equal to 0 to j equal to 1. Okay, so 12th line means transition taking from 11 to 12, and 6.
20 plus rotational constant 20 centimeter inverse.
Okay, I will check it. 15 to 60. Okay, so directly we can do calculation like this. Delta will be your, like here for this, your b 2j plus 1, and this is b 2j plus 1. So we have to take the difference. So here b 2 is to 11 plus 1, sorry, we have to take first 15 because higher energy, and then b 2 is to 11 plus 1, and this is 80 centimeter inverse. So we are getting here 31b and here 23b. Okay, so 80 centimeter inverse is equal to 8b. So b is equal to some, we are getting 10. How did you get 20? I'm getting 10. Did I do some mistake? Hello? Oh, sorry. I wrote the expression wrong. It's a 2b j plus 1, and this is also 2b j plus 1. So this is wrong. So we'll write here 2b 15 plus 1 minus 2b 11 plus 1. Okay, so we're getting some 32b, we're getting 24b, so it will be 8b, and here 80. Again I'm getting 10 centimeter reverse. So you check your calculation, please.
Yes, sir. Yes, sir.
It will be 10,
You're
correct?
right, sir. Yeah, sir. 10 centimeter inverse.
Okay, now we'll go to next question. This has a little bigger calculation. The first is the microwave spectrum of gaseous CN molecule consists a series of equally spaced line separated by this. What he is saying? Let's say we have a spectrum. So we have different lines, spectral lines. This is intensity. This gap is 3.7978, and we know that this gap is nothing but 2b. So b will be 3.7978 divided by 2. So it's 1.8989 centimeter inverse. Now how can we calculate bond length? So first we have to find the relation. So we know that this B is nothing but your H 8 pi square I C. Okay, and this I is your mu R square, correct? And this R is your bond length, so we have to calculate R. I by V. So from this expression, from this equation, we can calculate moment of inertia. From this expression we can calculate moment of inertia, and from this expression we can calculate bond length. So first we have to calculate I. Okay, so we can write like I H by 8 pi square B C. Okay, we'll substitute everything. 6.626 minus 34 joule second 8 3.14 1.8989 centimeter inverse 3 is to 10 to the power 8 meter per second. So we can convert this into the meter inverse. So I will write directly in the after conversion. I am dealing with SI unit, so that's why I will convert here. It will be 0.18989 meter inverse. Am I correct or wrong? So like 1 centimeter is nothing but here 10 to the power minus 2 meter. So 1 centimeter inverse 2 meter inverse. So we have to multiply. Sorry, it's wrong. So 1.8989 10 to the power 2 meter inverse. So we can write this value here. This will be cancelled out, and this. So finally we'll get something like a big calculation. I will see the. Okay, let me calculate then. For joule I can write kg meter square per second square. So this second square and this second will go. So we'll have kg meter square. Okay, I will do the calculation. 6.626 divided by. Can you help me in calculation? Can you tell me the answer? You will get 1.4742 10 to the power minus 46 kg meter square. So I we calculated from here. Okay, so you can see the power of rotational spectroscopy. So if, let's say we will have some unknown molecule, let's say we discover some unknown molecule, let's say AB, and if we know the reduced mass, then from rotational spectroscopy we can calculate the bond length, and this calculated bond length is very close to the other method. Okay, so we need here mu, that is reduced mass. So how we can calculate that? Mass of carbon, mass of nitrogen, mass of carbon plus mass of nitrogen. So it's given here everything. See, 12011 gram per mole, 14.007 gram per mole, and 1211 plus 14.007 gram per mole. So we can calculate like, see, this gram per mole will cancel out. We will get something. I change the color of the pen. Okay, 12,011 14.007 gram per mole. This will be as 26.018. Okay, and we have to multiply with Avogadro number because we need molecular reduced mass, not for one mole, for single molecule. So that's why we have to divide with Avogadro number. Per mole. Okay, so this will cancel out and you will get something 1.073723. This is plus minus 23 gram. So we can convert this in kg and you will get something. What you will get? In guess 1.0737 10 to the power minus 26 kg. Correct. Now I am writing here in this bracket. So what will be our bond length? 1.4742 10 to the power minus 46 kg meter square by 1.0737 10 to the power minus 26 kg, and then it will come around 1.1717 10 to the power minus 10 meter. So 1.1717 angstrom. The bond length of Cn will be, these are answer. So here we calculated for Cn, like in exam they can ask for anything, for CO, for HCl, for HBr. So that approach is, first you have to calculate the moment of inertia from your B value, from your spectrum, and then you have to calculate your reduced mass. Then simply by this expression you can calculate bond length. Got it, right? Okay, so this was little a big calculation. So the next question is, this will come later. This will come later. This question. So we understood here we understood how the rotational spectrum is generating. What are the conditions from rotational spectrum? What kind of information we can get? All those things. When it will be allowed? What is the significance of B? All this question we already answered. Okay. So we will see some of the application. So first is, what would be the effect of isotopes? Okay, let's say we will have HCl. So we are using atomic mass of hydrogen 1 and chlorine 35. What will happen to a rotational spectrum if we will replace this chlorine by 37, or if we replace this hydrogen by deuterium? What will happen? See, this hydrogen and deuterium are isotopes. Chlorine 35 and chlorine 37 are isotopes. So the question is, what will happen when we will replace one isotopes with other? So that's the topic come effects of isotopes. Okay, so before going to the all mathematics, first we will see this spectrum. This is rotational spectrum or microwave spectrum. For CO molecule. Okay, so there is one big peak here. You can see this one. but there are some side band also. See, there are small peak. The questions come in our mind, why we are getting these small peaks with very less intensity. So the y-axis is transmittance, x-axis is wave number. So transmittance is not 100%. Transmittance is around, see, 10% or some 8% something. Means other 90% is getting absorbed. Okay, but here the for a small peak, if you see here, the transmittance is around 90%, means absorbance is around 10%. So why we are getting small peaks? Because of natural abundance of carbon. So carbon, usually these isotopes majorly contribute, okay, but naturally we have C13 also. So because of this configuration is written here, C13 oxygen 16, we are getting this peak. Okay, see, because of isotopes. So let's say this peak is around, some 37 centimeters, let's say, but this is around 35, correct? So from a spectrum, before doing any mathematics, what we saw, when we are increasing the mass of isotopes, for example here, when we are changing carbon 12 from carbon 13, what we saw, the spectrum is shifting towards lower energy. Okay, so this is the conclusion we draw from the spectrum. Now let's try to understand mathematically. Okay, so we have two molecule, first one and the second one. So what we did, we changed the mass from m1 to m1 prime. Okay, and from lecture note we saw the reduced masses for this molecule mu and the reduced mass for this molecule mu prime. If you take the ratio of this, it will be less than 1 from lecture note. And we also know that this mu is inversely related to 1 by b. Okay. So if you take the ratio, if you take the ratio of reduced mass, what you will get, mu by mu prime is equal to b prime by b. So when you increase the mass, from m1 to m1 prime, this condition, the reduced mass ratio is less than 1, but if you see this equation, and we will replace this by this number, okay, less than 1. Okay, so what we observe, this rotational constant is for this molecule b prime, and this is for this. Detail is discussed in the lecture notes, so you should go there. So what we observe, this b prime is smaller than b. This b prime is smaller than b. Okay. So one line, by simply increasing the mass of the isotope, the value of rotational constant is decreasing, and we know that this energy is nothing but b j into j plus 1, correct? So when you will decrease this value, when you will reduce this b, this energy will decrease, correct? Obvious from this expression. So that's why you can see here, before any, like initially we will have this kind of energy level, but when we will replace this m1 with m1 prime, this energy level, the energy of this level will decrease. Okay, and that's why this value will shift toward left, toward lower energy. So in one line, what is the effect of isotopes? When we dope or when we substitute some isotope with heavier masses, what will happen? the value of rotational constant will decrease. As a result, the energy of the rotational lines, the energy of the rotational line will decrease. These are not rotational line, so we can plot like this. So this is your intensity and this is your wave number. It has very big application. Like, why do you simply want to do isotope substitution? So what is the rule? From this isotope substitution, we can calculate the abundance of, let's say I will compare C12 and C13. So because of this isotope effects or this isotope substitution, we can calculate the abundance for the carbon 12 and carbon 13, or let's say oxygen 16, oxygen 18. So these calculations were done in the lecture note. So calculations I am not doing, but based on this effect of isotopes, we have some questions. So I will go on that. So first question is the rotational constant for HCl35, HCl37 and DCl35. So here hydrogen and deuterium are isotopes. Mass are 1, 2. Okay. And here you have chlorine 37 and chlorine 35 isotopes. Isotope means same atomic number but different mass number. Okay. Then what will be the value of, can you calculate this? What will be the order? Or you can write this one also. This B is related to H 8 pi square I C. So I we can write 8 pi square mu R square C. So for all the molecule, it doesn't matter if you will replace this isotope with heavier isotope, the bond length will not change that much. Like it will be very minor change or no change at all. Okay. So this R will be constant. C is velocity of light. This H is constant. This pi is constant. The 8 is constant. So the B rotational constant is inversely proportional to 1 by mu. Among three molecules, the molecule having highest reduced mass will have lowest rotational constant. So now can you calculate it?
One number, sir.
Are you sure?
Yes, sir.
No, it can't be one. Okay, I will try to calculate.
Calculate the sir.
See, if you write here 1 plus 35, oh sorry, multiplied, and 1 plus 36. Okay, and for the second case, I will say mu1, mu2, 1, 37, and mu3, 2, 35, 2 plus 35. So this is like 35 divided by some number. Okay, and this is 37 divided by some number, 38, and this is of course 70 divided by some number. So this will be highest, mu3 will be highest. So this will have lowest rotational constant. Got it right?
Yes, sir. जी sir.
So उसके हिसाब से कौन सा ऑप्शन हो जाएगा? There are two options which have lower rotational constant.
37/36.
D or B?
Yes, sir.
B
D
will
or
be,
B?
B will be a correct answer.
B. Yes.
B.
B, sir.
Yeah.
Okay.
So next question. So there are three energy level with rotational number 1, 2, 3. In absence of any external perturbation, identify correct option. External perturbation means if you are not giving any light, the all energy level so what is mj I will see in the incoming lecture, but for now there won't be any rotation, so this all mj will be have same value. But what is mj we will see in the next slide. What is mj? So here we understood like many things, how to interpret a spectra, how can we plot a spectra, and from rotational spectra what are the information we can get. Now next question come degeneracy. Okay. So before going to the degeneracy, let's say I will draw some peak. I will go to previous slide. Okay, some back slide here. If you see here this peak, the intensity of for this peak is lesser than this, and the intensity of this peak is lesser than this. So why we have different intensity then? So can we calculate really which transition will have maximum intensity? So to do that, to calculate the intensity of the transition, we can do using Maxwell-Boltzmann distribution. Okay, Maxwell-Boltzmann distribution, which is given by Nj by N0 is equal to Gj, and this Gj is nothing but degeneracy of jth level. Now we will see what is this J and how, like where is coming from, what is the origin of this J. Okay, so we know that energy is nothing but L square by 2I, L square by 2I, and this L is given by J into J plus 1 H card. Okay, here this L, this angular momentum for the rotation of molecule, angular momentum for the rotation of molecule is quantized, meaning it cannot have any discrete value, there must be some integral value. So okay, so this is the unit of h by 2 pi. Okay. So if you see this angular momentum, it will have two component. Okay, this is vector, this angular momentum is vector, so it will have magnitude as well as direction. Okay, and direction is given by thumb rule. Let's say the molecule is rotating around this axis, so we can give like this, and like anti-clockwise then we can give like this molecular axis positive up, or let's say molecule is rotating clockwise, then this will be your molecular axis. Okay. So the direction for the rotation can be given by right hand rule, or hand rule, simply we can say right hand rule. Okay. So for any rotational level, for any rotational energy level, there can have different rotation, which will have similar energy. So what is the meaning of degeneracy? Let's say I will draw some energy level diagram here. Let's say this is energy level, and let's say here we have two energy level. So this two energy level has same energy, so this we call degenerate. Okay, now here degeneracy is coming because of direction of rotation. Okay, direction of angular momentum. Okay, so there can have different direction for the molecule. Okay, let's say molecule can rotate like this, or it can rotate like this. Okay, so for the different rotation we will have different direction of the angular momentum, and that will give rise degeneracy. For example, let's see here. Okay, let's say we have one molecule, this dot represent atom. So let's say this atom is rotating on this circle. Okay, and this is your z axis, so it's rotating around z axis like this. Okay, but this is z axis, sorry, this is your axis of rotation, sorry, this is your axis of rotation. Okay, and we saw there that this LZ, this like angular momentum on z axis is nothing but L cos theta, and this L is given by under root j into j plus 1 cos theta in unit of h cart, and we can write this whole term by we can replace this whole term by mj. Okay, so here we can write cos theta, this will go in the denominator, so it will be mj h cart and divided by under root j into j plus 1. And we saw that the value of cos theta can be between minus 1 to plus 1, and once we get the cos theta and we find that the mj value can be minus j to plus j, and in total 2j plus 1 for degeneracy. What is the meaning of this 2j plus 1? What is the meaning of mj? So let's say we are in j equal to 1 state, j equal to 1 state. Okay, like we are showing here j equal to 1 state. So what will be the value of mj? It will be plus 1 0, so ulta will go minus 1 0 plus 1. So we have three possible value of mj, meaning we will have three direction for the angular momentum. Okay, so let's say we have this is our molecule, and the direction for the angular momentum is perpendicular to the molecular axis. So this is your molecular axis, this one. Okay, and the direction is perpendicular, direction for L is perpendicular to the molecular axis. And what is angular momentum? What is the magnitude of angular momentum? That we can calculate using this equation, this one. See, so L we can calculate, we can put 1 plus 1 1 in the unit of h cart. So I'm not writing this in the unit of h cart, so this is nothing but your under root 2. So for this angular momentum you have magnitude under root 2 in the unit of h cart. I'm not writing again, and let's say it's rotating at this line. Here is your molecule, here is your molecule, dotted line. Again, the angular momentum vector will be perpendicular to molecular axis. So this is our angular momentum axis, perpendicular. We have this line and we have this line, perpendicular. Okay. Again, the magnitude for this angular momentum is under root 2, but the projection of this angular momentum on z axis should be minus 1. That is the meaning. Meaning it will rotate like this in a circle here. Okay. So at every time, let's say we draw here, let's say we draw here, let's say we draw here, any direction, the projection on z axis should be minus 1. That is the meaning of mj. We can have other configuration also. Let's say our molecule is here in this axis, and again the angular momentum vector will be perpendicular to molecular axis. So this is our angular momentum vector, and the magnitude for this vector is under root 2. See, I already wrote here, but the projection of this vector on z axis should be plus 1. Okay, see, there are three rotation possible, like there are three directions for the angular momentum, but all have same magnitude. See, again there are three directions for angular momentum, but all have same magnitude, and this L is directly related to energy. We saw L square by 2I. So this L is same, means energy will be same for all this rotation, correct? And that's why we call degenerate state. They have same angular momentum magnitude, meaning they will have same energy but different direction, and this arises degeneracy. Okay, so for j equal to 0, let's say your molecule in the ground state is in the ground state, what will be your degeneracy? What will be mj? 2j plus 1, correct? So if you substitute here j0, it will be 1, meaning in the ground state we don't have any degeneracy. Okay, understood, right? So let's say I will take another example, j equal to 2. So what can be the possible value of mj? Second, mj will be here -2, -1, 0, +1, +2. We will have 5 value. Or degeneracy we can calculate 2j plus 1, and then again 2 plus multiplied by 2 plus 1, so we will have 5-fold degeneracy. Okay. Again, this theta value, this theta, like this, let's say this vector, this one is making some angle with this z axis, correct? This theta, and this theta can be calculated using this equation. So you cannot have any random theta. Okay, at every direction, let's say you have here, or you're here, or you're here somewhere. At every point you should have same theta, so this theta can be calculated. So you cannot have some random rotation, there must be some fixed angle also. Okay, so degeneracy, if you try to draw from this line, let's say we have like z axis or laboratory axis, we say this, then let's say we have molecule, one diatomic molecule like this. Okay, and this is our angular momentum L, and what will be magnitude of angular momentum? 2 plus 1 in the unit of h cart, so you'll get some 6. Okay, so the magnitude will be under root 6. Okay. Now we can have here, in such a way, your molecule can be like this, and this is your vector, it's in angular momentum vector, so it should be perpendicular. In such a way, the projection at this axis should be +1. Similarly, +2. Similarly here, -1, -2. So you'll have something like this. See, you have 5 different directions for angular momentum vector, but all have same magnitude, under root 6, under root 6. So all will have same energy. That's why we call degenerate state. Okay. Now coming back to some problems based on these discussions. So the first question is degeneracy of rotational energy level J equal to 3. So you can draw here. So first I will calculate, then I will draw what is the meaning of that. Okay, so J is 3, so degeneracy will be J, what was degeneracy? I forgot. 2J plus 1. So 2 is to 3 plus 1, meaning 6. This is answer. And if you try to draw this energy level diagram, how can we draw it? So this is like first 0 level, and here 1, 2, 3. So can you tell the degeneracy in J equal to 1? Three, right? So there will be 3 level which have same energy. Okay. For 2 we will have 5 such like states, and for 3 we will have 7. Okay. So there will be 7 energy states which will have, so 7 rotational states which will have same energy. So this is the meaning of degeneracy. So this will have same energy. It's looking like it has different energy, but they will have same energy like this. So the next question is, the energy of a rotational level is given by 12 centimeter. What is the degeneracy? How can we calculate this? The energy of rotational energy level is 12 centimeter inverse. Okay. What is degeneracy then? Can you calculate this? So to find degeneracy, we need to find J, correct? And from this information, from energy level, we can find J. How? Let's see. So we know E is nothing but your J, J plus 1, J plus 1 in the unit of H card. So I'm not writing that H card. Okay. So let's say we'll do a square both side. We'll get something J square plus J square plus J, and this I will take this in that side, so it will be we will have 12 equal to 0. So J square plus J, so we can write like this: J square minus 12 square plus J 0. Excuse me. And what will be the value of J here? Answer is not coming correctly. I need to check. I will check this problem because we are getting some j equal to 6. So this should be 6 is to 2 plus 1, 13. But there is no option like this. So I will check on this. I am not sure. Sorry. So coming to the next question. The degeneracy of rotational energy level. Rotational level J is 3. Degeneracy is 3. And the transition between J double prime to J double prime plus 1 has energy in centimeter in a hertz. So how can we calculate that? The degeneracy is 3. So 2J plus 1 is 3, meaning J equal to, is that 1. Okay. Now we know delta E, we can simply directly calculate 2B J plus 1. So it will be your 4B. Or detail we can write here J equal to 1. So transition is happening from J double prime equal to 1 to J double prime plus 1, means 1 to 2. Transition is happening 1 to 2. So we can calculate delta E. The energy for this one is B 2 2 plus 1, because the energy can be given by this expression, minus B 1 1 plus 1. So 6B minus 2B equal to 4B. So by given this degeneracy, we can calculate the energy difference. So it will be 4B. So we have started by saying that can we calculate the population which has, can we calculate the energy level which has highest population. We have started by saying that, and we wrote this Boltzmann distribution with something like Gj minus delta E by Kt. Sorry. See, if you will plot this distribution, this relative ratio against degeneracy, you will get something like this. This is, so here we have maximum probabilities, maximum intensity. Maximum intensity means at this rotational level we will have maximum transition, meaning at 2 or j equal to 3 or j equal to 4 we will have maximum number of molecule, because this intensity is directly proportional to concentration. So the rotational energy level having highest number of concentration or highest number of molecule will give highest intensity. Okay, so we can calculate using this expression by solving the all the expression here, this kind of expression, all the expression, this one, we can get J in the form of like this. So by using this expression, you can say in this rotational energy level we will have highest transition. Let's say from J equal to 3 to J equal to 4 we have highest transition. Okay, so can we calculate this? So J max is, what is the formula? Kt by 2hCb to the power minus 1 by 2. So K we know, correct? What is the K? K is Boltzmann constant. So what is the value of K? 1.38 10 to the power minus 23 joule per Kelvin. And what is the temperature here? 300 Kelvin. 2 we know H 6.626 minus 34 joule second, and the velocity of light is, we are keeping everything in SI, so that's why I'm writing meter per second, and the value of B is given this much. So in meter inverse it will be 5.66 10 to the power minus, sorry, plus 2 meter inverse. Okay, so this whole root to the power 1 by 2 minus 1 by 2. So if you will solve this, you will get something like 7.56, which is equivalent to 8. So J max 8. So what is the meaning of that? Let's say we draw the energy level here. E, this is 0, 1, 2, 3, 4, 5, 6. I will write here 7, 8, 9. So J max is equal to 8, meaning we have highest population here, means highest सबसे ज़्यादा molecule यहाँ पे होगा. What is the meaning of this? This transition will be most populated, meaning the intensity of the rotational line because of transition from j equal to 8 to j equal to 9 will be maximum. Okay, so this is, let's say we have rotational spectrum intensity and this is your wave number. So because of transition between 8 to 9, we will have maximum intensity. Got it? Any doubt till here? Because this is the last slide I have. Any question, anything, any doubt, any topic, in any topic? Let me stop the recording.